Scientists at 3 major universities proved bacteria from ordinary soil can turn urine and sand into solid stone. DARPA confirmed it works in the field. The process costs $0 in raw materials. A cubic yard of commercial concrete runs $150 to $200. It requires cement plants, quarries, diesel trucks, and a functioning industrial grid. Biocemented material uses sand from the ground, bacteria cultured from dirt, and the one liquid every human produces daily for free. By the end of this video, you will know exactly how to culture the bacteria, prepare the sand, apply the solution, and cure structural material without buying a single product from anyone. And that's exactly what we do here. We recover verified knowledge that the system buried. Not speculation, not theory. Peer-reviewed research, your taxes paid for, military-tested techniques they never taught you to use. We source everything, we cite everything, and we give you the exact steps. If you want to stay informed on knowledge that matters when supply chains fail, subscribe now. Because what's coming next will make you question everything you thought you knew about construction. Let's start with why this isn't actually new, and why the ancient version outlasted everything we build today. The Pantheon in Rome has stood for nearly 2,000 years. Its concrete dome remains the largest unreinforced concrete dome ever built. Modern engineers study it because they cannot fully replicate its durability. The Roman harbor at Caesarea still shows breakwater structures that survived 2 millennia of wave action. 20th century Portland cement structures begin degrading within 50 to 100 years. The difference wasn't just skill, it was the binder. Romans used volcanic ash, but cultures across continents independently discovered that biological materials created superior construction binders. Blood proteins in mortar, milk casein in plaster, plant resins in adobe, animal urine in rammed earth. These weren't primitive improvisations. They were functional technologies that worked for thousands of years. Then the 20th century arrived. Industrial Portland cement offered something biological binders couldn't match: speed. Pour it, wait hours, move on. Economics rewarded fast construction. The biological methods were abandoned, not because they failed, because they didn't suit quarterly earnings reports. But scientists in the late 20th century started asking questions. Why did those ancient binders last so long? What was actually happening at the molecular level? They found their answer in microbiology. In the 1990s, researchers identified specific bacteria with extreme urease activity. The bacterium got its name, Sporosarcina pasteurii. Common, non-pathogenic, present in alkaline soils worldwide, and capable of something remarkable. By the early 2000s, university labs were running controlled demonstrations. UC Davis published results. Murdoch University in Australia replicated them. Ghent University in Belgium confirmed the findings independently, all peer-reviewed, all showing the same process. The bacteria colonize sand. The urease enzyme they produce hydrolyzes urea. That creates ammonia and carbon dioxide. The ammonia raises pH. In the presence of calcium ions, carbonate ions precipitate out as solid calcium carbonate crystals. Those crystals fill the spaces between sand grains. The sand turns to stone. It's called microbially induced calcite precipitation, MICP for short. And it works exactly like the biological binders ancient cultures discovered through trial and error. Except now scientists knew the precise mechanism, so universities proved it in the lab. But was anyone willing to test it where it actually matters? In the field, under real conditions? Yes. And you've already paid for that research with your taxes. What you're seeing right now is the summary. The full research behind this topic and hundreds of other techniques lives in the vault. Water purification the EPA stopped talking about. Bomb food preservation methods that predate refrigeration. Defensive strategies pulled from military manuals. Medical protocols sourced from field documentation. All organized, all cited. No filler, no hype. Just sourced research you can act on when the systems you depend on stop functioning. The link is in the description. But everything you need to actually do this biocementation process is coming right now in this video. Stay here, because this is where it gets interesting. DARPA funded research into biological construction materials as part of their engineered living materials programs. The Defense Advanced Research Projects Agency, the same people who developed the internet and GPS, they wanted to know if bacteria could create structural materials in field conditions without industrial infrastructure. The U.S. Army Corps of Engineers tested MICP for soil stabilization, dust control on unpaved runways, expedient fortification, real-world field conditions, not climate-controlled laboratories, forward operating bases where supply chains are unreliable and construction materials are scarce. The results were published in military engineering journals, confirmed, validated, documented with measurements, compressive strength achievable, several megapascals. That's the unit engineers use to measure how much force material can withstand before it fails. For context, rammed earth averages 1 to 2 megapascals. Fired brick ranges from 5 to 20 megapascals depending on clay and firing temperature. Standard structural concrete ranges from 20 to 35 megapascals. Bio-cemented sand with adequate treatment cycles reach the low end of fired brick, sufficient for walls, foundations and low-rise construction, paving, protective structures, blast barriers, perimeter fortification. The military tested it, published the data, confirmed it works, and then filed it away. Let me walk you through what's actually happening at the chemical level so you understand this isn't magic or wishful thinking. It's predictable biochemistry. You start with sand, silicon dioxide particles, lots of empty space between grains, no binding agent. Pour water on it, and it flows apart. You introduce Sporosarcina pasteurii bacteria. They colonize the sand surfaces. They're looking for nutrients. You give them urea. That's a nitrogen compound. Your body produces it as a waste product. It's in urine. It's also available as agricultural fertilizer. The bacteria have an enzyme called urease. Extremely high urease activity in Sporosarcina pasteurii compared to most other bacteria. The enzyme breaks down urea molecules. One urea molecule becomes 2 ammonia molecules and 1 carbon dioxide molecule. The ammonia raises the pH of the surrounding environment, makes it alkaline. The carbon dioxide dissolves into carbonate ions. If calcium ions are present in the solution, chemistry takes over. Calcium ions and carbonate ions combine. They precipitate out of solution as solid calcium carbonate. That's limestone, the same mineral that forms stalactites in caves, the same mineral that makes up chalk and marble. It crystallizes between the sand grains, fills the pore spaces, binds everything together. Repeat the process, more bacteria, more urea, more calcium carbonate crystals. The binding gets stronger. The sand becomes sandstone, solid, weight-bearing, structural. The process has been measured, documented, peer-reviewed, published, and confirmed by the United States military in field conditions. So it's proven, it's free. The military uses it. So why can't you? Here's the mechanism of exclusion. And it's not a ban. The International Building Code and International Residential Code govern legal construction in most jurisdictions. They reference standards published by ASTM International, American Society for Testing and Materials. When an engineer designs a structure or a building inspector approves construction, they verify that materials meet specific ASTM standards. There is no ASTM standard for biocemented material. None. The testing protocols don't exist. The material classification was never created. No ICC evaluation service report has ever been issued. A building inspector cannot approve it. A structural engineer cannot stamp drawings specifying it without massive professional liability exposure. It's not illegal, it's just outside the regulatory framework entirely. And that framework was built by and for industrial material producers. The International Code Council develops the building codes. Their board includes representatives from material manufacturers. The cement industry is worth hundreds of billions of dollars annually. Multi-$100 billion market. Major multinational corporations, their business model depends on continued demand for Portland cement. Cement production is responsible for approximately 8% of global carbon dioxide emissions, while 8% of the entire planet's CO2 output comes from making the binder in concrete. Massive environmental cost, massive energy requirement, limestone quarrying, high-temperature kilns burning fossil fuels, transportation networks, all of it necessary to produce a material that degrades faster than what Romans built 2,000 years ago. You're paying $150 to $200 per cubic yard for that material. It requires industrial infrastructure, reliable electricity, fuel for kilns and trucks, functioning supply chains, regulatory approval because the system was designed around it. Biocemented material uses sand from the ground, bacteria cultured from dirt, urea from urine or agricultural fertilizer, calcium from dissolved limestone, chalk, eggshells, or wood ash. Total cost, effectively $0 per cubic yard in raw materials. And the reason you didn't know that isn't because it doesn't work. It's because no one with power benefits from you knowing it. Now, here's the honest part. What this can and cannot do. Strength variability is inherent in biological processes. Laboratory conditions produce consistent results. Field conditions with temperature fluctuations, varying calcium availability, and inconsistent moisture produce variable results. You're working with living organisms, not industrial chemistry. Expect variation. Ammonia off-gassing during the curing process is a real hazard. Ammonia is toxic in enclosed spaces. This is an outdoor process or a very well-ventilated space. Don't cure biocemented material inside a sealed room. The ammonia will build up. That's dangerous. Calcium source is required. Without sufficient calcium ions in the solution, the bacteria can metabolize urea all day and you'll get weak or incomplete cementation. You need dissolved calcium, Calcium chloride works best. Crushed limestone or chalk dissolved in water works. Eggshells dissolved in vinegar, then neutralized works. Wood ash dissolved in water works but less efficiently. No calcium means weak results. This material is weak in tension, like all concrete. It resists compression well. It handles weight pressing down. It does not handle bending or pulling forces. You need reinforcement for any application involving flexural loads. Rebar, bamboo, fiber mesh. Anything carrying tension stress needs reinforcement. The process is slow compared to commercial concrete. Commercial concrete sets in hours. Biocementation requires repeated treatment cycles over days to weeks depending on target strength. 5 cycles might take a week. 20 cycles might take a month. You're not pouring a foundation on Monday and framing on Wednesday. Calcium carbonate is susceptible to acidic water over time. The binder can dissolve slowly in low pH environments. Don't use this for structures in constant contact with acidic groundwater. Surface exposure to rain is fine. Submersion in acidic water is a problem long term. These are real constraints, but compare them to having no building material at all when the supply chain is gone. This isn't meant to replace your local concrete plant. It's meant to exist when that plant doesn't. Here's exactly how to do it. Step 1. Culture the bacteria. Collect soil samples from alkaline environments. Look for areas with high pH near limestone deposits. Around concrete foundations where lime has leached into soil. Alkaline soil favors Sporosarcina pasteurii growth. Prepare a growth medium. Use warm water. Add urea, 2 to 3% concentration by weight. That's about 20 to 30 grams of urea per liter of water. Urine works directly, but dilute it. 1 part urine to 3 parts water for better results. Add a nutrient source. Sugar works. Boiled vegetable scraps and water work. Molasses works. The bacteria need carbon and energy. Mix soil samples into the growth medium. Incubate at approximately 30 degrees Celsius. That's about 86 degrees Fahrenheit. Room temperature in warm climates. Slightly heated in cooler areas. Don't exceed 37 degrees Celsius or 100 degrees Fahrenheit. Wait 48 to 96 hours. The liquid should become cloudy. That indicates bacterial growth. You now have a culture rich in active urease-producing bacteria. If it smells like ammonia, that's confirmation the bacteria are metabolizing urea. That's what you want. Step 2. Prepare the sand. Use clean sand, coarse to medium grain size. Avoid fine sand. Avoid clay-heavy soil. You want silicon dioxide particles with space between them for the calcium carbonate to fill. Place sand in forms or molds, whatever shape you want the final material to take. Wooden forms work, plastic containers work, excavated ground works if you're creating a floor or a foundation pad. Compact lightly, not densely packed. You need pore space for the bacteria and solution to penetrate. Step 3. Mix the cementation solution. Or combine your bacterial culture with fresh urea solution and calcium source. Equal parts bacterial culture and calcium solution works as a starting ratio. For calcium source, dissolve calcium chloride in water. 10 to 20% concentration works well. Calcium chloride is available as a de-icing agent or from chemical suppliers. Alternatively, crush limestone or chalk into powder and dissolve in water acidified slightly with vinegar. Then neutralize with baking soda. Less efficient, but functional. Eggshells dissolved in vinegar, then neutralized work. Wood ash dissolved in water provides some calcium, but lower concentration. The goal is a solution rich in active bacteria, urea for them to metabolize, and dissolved calcium ions for precipitation. Step 4. Apply and repeat. You pour or spray the cementation solution over your sand substrate. Ensure even coverage. The solution should saturate the sand but not create standing water pooling on top. Allow 12 to 24 hours per cycle. The bacteria need time to colonize, metabolize urea, and precipitate calcium carbonate. Reapply. Same solution mixture. Saturation again. Wait another 12 to 24 hours. Repeat. 5 treatment cycles will produce noticeable hardening. 10 cycles produce moderate strength. 20 plus cycles produce maximum strength for this process. Keep the substrate moist between cycles, not waterlogged, not dried out. Moist. The bacteria need water to remain active. If the surface dries completely, the bacteria die and the process stops. Step 5. Manage curing conditions. Optimal temperature range, 20 to 37 degrees Celsius. That's 68 to 99 degrees Fahrenheit. The process slows significantly below 15 degrees Celsius or 59 degrees Fahrenheit. It stops near freezing. Maintain humidity. Cover with damp cloth or plastic sheeting between applications. Prevent rapid evaporation. Avoid direct sun drying the surface prematurely. The bacteria need moisture. If you're working in hot, dry climates, shade the work or apply treatment cycles in early morning and evening. After final treatment cycle, allow at least 72 hours of moist curing before exposing to load or drying completely. Expected results. Compressive strength of several megapascals with adequate treatment cycles in good conditions. suitable for non-load-bearing partition walls. Low-rise construction foundations, paving for foot traffic or light vehicles, protective barriers, perimeter walls, garden structures. Anywhere you need solid material and can accept the time investment. Sand, bacteria from dirt, calcium from rocks or shells or ash, and the one thing your body produces every day that you flush away without thinking. The Romans built with biological binders that stood for 2,000 years. Everything modern industry produces degrades within a human lifetime. Scientists identified exactly why the ancient method worked. They proved it in peer-reviewed studies. Named institutions: UC Davis, Murdoch University, Ghent University, multiple countries. Independent replication. The United States military tested it in field conditions. DARPA funded the research. The Army Corps of Engineers validated it. And published the results. Confirmed compressive strength sufficient for real-world construction applications, and then did nothing to create a civilian pathway. The building code excludes it, not because it's dangerous, not because it fails, because the regulatory framework was built around industrial products sold by corporations with hundreds of billions of dollars in annual revenue. Cement production creates 8% of global CO2 emissions. You pay $150 to $200 per cubic yard for material that requires quarries, kilns, trucks, and a functioning grid. The alternative costs $0 in raw materials, uses resources already under your feet and inside your body, works through predictable biochemistry that's been peer-reviewed and military tested. You now know the process, the bacterial species, the chemical mechanism, the step-by-step protocol. No supply chain required, no purchase necessary, no permission needed for knowledge. Share this. The person who needs it most might not find it on their own. They're not searching for biocementation or microbially induced calcite precipitation. They're searching for how to build when everything else is gone. Next time we're looking at water purification methods that predate chlorination, techniques that worked for armies in the field before chemical treatment existed. The research is already done. The vault has it. And you're going to want to know it before you need it. A bucket, some dirt, sand, and what your body produces every day. The knowledge was always there. They just made sure you never learned to use it.